Alright, well welcome back, Algebra 1 students. We are going to be doing graphing right now in Chapter 8. Chapter 8 is all about graphing quadratic functions. And so we can see here for 8.1 we're graphing f of x. That's our function notation. It's the same thing as if we would say y is equal to ax squared. And we're going to just take one piece at a time of this function. So you can see as we kind of go through all of Chapter 8, here's our whole list of what we would look at in Chapter 8. We start by just building at the beginning of just the ax squared, then we add in a little extra, then we add in some more, and then we change it up a little bit. So we're just taking one step at a time, but they're all quadratic functions. They're all going to look the same as far as the shape of the graph and all that. So 8.1, we're identifying characteristics of quadratic functions. So that's what we got to look at first, is identifying some of those characteristics, some of the basic characteristics, and then we're going to do some graphing of this form, and it's just going to be in this form. As we get into the further lessons, like I showed you, we're going to get into the form a little bit, adding on to a B and a C term as well. First, let's go on to our cartoon of the day. So here in this cartoon, we see how birds see the world. So birds see the world, I guess, apparently with bullseyes on top of people's heads and on top of the dog's back. Those are their targets from up above. Alright, I always enjoyed that cartoon. Alright, well, in page 247, you'll see your vocabulary, and here's where we're going to look at these identifying characteristics of quadratic functions. Kind of need to start there. Just what is a quadratic function? And you could write this down for that. It is a non-linear function. Now, we've done linear functions already at this point, and linear functions are just those straight lines. Y equals mx plus b would be that slope-intercept form equation. That's like the graphing form of that equation. We could look at a standard form as well of the linear, but we've done all the linear ones. Now we're going to look at quadratic functions, and so these are non-linear functions, and they can be written in the standard form of this. So here's our standard form of a quadratic function: y equals, or you could use f of x, and it says ax squared plus bx plus c. And like I said, we're just focusing on just this first part here, ax squared part, and eventually we will add in the b and then we'll add in the c as well. The name of this graph, as you can see, the shape of it is a U-shape down here. Here's our shape. It's not a line like the linear. It's a U-shaped graph, and it actually has a special name. It's called a parabola. So you can just write down next to that vocabulary word of what a parabola is. It's the U-shaped graph of a quadratic function. There are, a couple graphs that we might see along the way in algebra that do have special names. Most of them don't. You would just name it as a shape of a line, or whatever the shape might be. But this one, it's a U shape, but we can call it a parabola. And this is the parent function. As you can see here, the parent function of this graph would be right here. This is what it would look like on the actual coordinate plane. And in the function equation, it would look like this: f of x equals x squared. That's a very important thing right there. You want to highlight that this is the parent function of the quadratic. It's the most basic. If it was a linear function, it would just be f of x equals x. Plain old x is the basic one for a linear. Well, the basic one and the parent one for the quadratic is x squared. Just a 1x squared. And that's what it would look like if we were graphing it. Now, as we look at this graph, there's the characteristics that we need to understand. The very first characteristic is what's called the vertex. The vertex would be this point right here, which is either the highest or the lowest point. In this particular one, it would be the lowest point, since it's opening this way, going up. And as you can see and notice that you have two arrows on this graph. They're both going up. On the linear function, you kind of had arrows on each end of that line. Well, we have an arrow on each end of this as well. It just happens to be they're both going in the same direction on a quadratic function. And so that allows you to have this highest or lowest point, and that's called the vertex. You could also call it a maximum or a minimum point. In this case, it would be the minimum point of this function is right here at this vertex point. And we can identify that here as 0, 0. That is at the origin. It's 0, 0 on the parent function. And really what this vertex does, it's right in the middle of the function. And with that, we can understand the axis of symmetry just the word axis is like a x-axis or a y-axis. This is an axis of symmetry. Well, symmetry cuts it right down the middle into two equal halves. That's what it does here. It's symmetrical. This half is exactly the same as the other half on the other side of the line of symmetry or axis of symmetry. Sometimes they might call it the line of symmetry as well. So those are two important things. Now we would describe this axis of symmetry in terms of an equation. In this case, the equation would be x equals 0. It's always going to be x equals, because it's going to be, in this case, a vertical line going right down through the x at 0 in this case, so that's why it's x equals 0. A couple other things we could see is the decreasing, increasing part, and that's always based on going from left to right. So as you're going from left to right, we would start here and come down, so we'd actually be coming down the function and decreasing, as you can see the arrows going in this direction, and then once we hit the vertex, then we start to go up and it's now increasing. So in this case we would say that we are decreasing when x is less than 0. This on this side of the axis of symmetry, it's less than 0. On this side of the axis of symmetry, which means x is greater than 0, we are increasing. So that's how you can describe the location of where you're increasing and decreasing. All right, let's go ahead and look at an example of one of these. Again, you don't need to write this down, but just go and watch this. So in this graph, we can see our vertex here is a different point than 0, 0. It's now this point, -1, -2. It just moved over here, which means the axis of symmetry is not 0 either. It's always the x-coordinate of the vertex. X equals -1 is the axis of symmetry. Now you describe it always as an x equals equation. And then you're increasing right here. Your increasing you're decreasing first, just like we were before, and it's going to be less than the -1, less than this axis of symmetry. So basically you're using this, just putting a less than symbol here. When you're less than -1, we are decreasing, and when we're greater than -1, we're increasing. You can also see the domain and the range from this as well. The domain, again, is asking you, where's the graph on the x-axis? In this case, it's all real numbers, which means it's everywhere. That's why this arrow keeps going to the left as it goes up. This one keeps going to the right as it goes up. And so the graph is everywhere on the x-axis. For the range, where's the graph on the y-axis is the question for the range. And you can see it's not everywhere. It's only from the vertex up and above. And so in that case, we would describe it more like an inequality. It is really greater than or equal to the -2. This is the y-coordinate of the vertex. So y is greater than or equal to -2 would be our range. All right, so let's go ahead and look at a couple extra practice problems, number 1 and number 2 on page 248. I'm going to go ahead and give you a chance to do these. You need to answer basically everything here. What is the vertex? What is the axis of symmetry? What is the increasing and decreasing? What is the domain and the range? So those 6 things, just answer that for number 1 and answer them for number 2, and then go ahead and play it to see if you are correct in answering all of these 6 different things here. So go ahead and pause the video and try number 1 and 2 by identifying all the characteristics of each of these quadratic functions. Alright, so hopefully you have now tried these and put an answer down for each of these. Let's go ahead and start with the vertex on number 1. What's the vertex? That would be just the point that would be right there. So you can see that vertex is the ordered pair -1, +1. Your vertex is always an ordered pair. That's that point. It's the point right there. It's the lowest point there of that parabola or that quadratic function. The axis of symmetry is going to be a line that would go straight down through that vertex point right there at -1. So it's x equals -1. That would be your axis of symmetry. Where is this? Where is it increasing? So you can see it's increasing right here as it goes up. So it's going down first, then it's going up. So when it's greater than -1, it is increasing. And when is it decreasing? Well, that's going to be on this side of that axis of symmetry line, which has been when x is less than -1 is when it's decreasing. Our domain for this, and the domain for every parabola, every quadratic function is going to be the same. It's going to be all real numbers. So each one is all real numbers. You could use infinity symbols, in fact, even to say it's going from -infinity to +infinity. That means all real numbers. It's everywhere. The range on this one is only above the vertex, so that on the y there, that's a +1. So it's greater than or equal to 1. Now this one's the equal to because it's actually equal to, because that point right there, your vertex, is sitting on positive 1. So it is equal to. These ones would not be equal to. You can't be equal to right here at the vertex. It's only less than or greater than from that axis of symmetry. Number 2, our vertex on this one, way up on the top, it would be a maximum point here. The highest point would be your vertex. It's an ordered pair. 3, 4 is that point right up there. X is 3, Y is 4. The axis of symmetry is going to be going right through the middle of that, and that's going to be at 3, so X equals 3 is your axis of symmetry. And the increasing and decreasing, so again, going from left to right, so we're starting on the left arrow, we're actually increasing first. So we're increasing on this side, so when X is less than the 3, when X is less than 3, we're increasing, and then once we pass 3, and now X is greater than 3, going this way, we are decreasing, we're going down. Our domain, like before, is all real numbers. Everyone will be the same for domain. But the range is going to be really the vertex and below, so it's less than this 4. So less than or equal to 4. It can equal 4 because you're sitting on 4 at the vertex, and it's also less than 4. That's where your range is. That's where the graph is on the y-axis. All right, let's get into actually now trying to graph some. So here's a core concept for on page 248. So if you go back a little bit, you can see that. So what we see here, and it might be a little confusing because we actually have 3 different graphs graphed on the same coordinate plane here for each one of these. So let's kind of take a look at one of them is going to be our parent function. So that's going to be the blue one. The blue one would be actually be the parent function. So what we're showing here is really the difference with your A number, the number in front of this, when that is greater than 0, and also when it's less than 0. So that's where there's 2 different things here. So sometimes you're going to see them opening up. We even just saw this on 1 and 2 here a second ago. Sometimes you see that parabola, that U-shape opening down. Well, how do you know when that's going to happen? Well, it's going to open down basically when there's a negative. A is less than 0, that means it's a negative. When there's a negative in front of here, that means it's going to be opening down. So basically when your A number, or there's a negative in front of your x squared, you could see, I'll just go ahead and put it down here. Basically when you have a negative in front of x squared, like that, that's when it's going to be opening down. If there's a positive in front, then it's going to be opening up. Now what about the difference between the 3 here? Well, like I said, the blue one is the parent function. Sometimes you're going to be on that green one where you're a little narrower. It's a little thinner than the parent function, so it changes the shape a little bit, as you can see. Sometimes it makes it narrow, sometimes it makes it wider on the red one. Well, when it makes it narrower, that means your A is greater than 1, in fact. So just the number itself. So we're talking about the sign. So based on the sign, whether it's positive, it's opening up, negative, it's opening down. So we maybe want to put this right here. So you can put positive right here. Just put POS for positive, and then this would be a negative down here. That's how you know if it's opening up or down. So positive opens up, negative opens down. I can put opens here. Opens up. And this one's going to open down. So negative, it opens down. But what about these when it's the different shape? It's narrower and thinner right here when your actual number, when the number in front, when the A number is greater than 1. So if it's like 2 or 3 or 4, then it's going to get narrower and thinner than the parent function. But if it's going to be right here between 0 and 1, so like a decimal, between 0 and 1 would be like, in terms of money, we would think of it as just some change. Like 1 penny to 99 cents. You know, that's between 0 and 1. So if you have like a penny, it's going to be wider. If you have 99 cents, it's still going to be wider than the parent function. Once you get to the dollar, right? 1, right? Once you get to $1, it is the parent function. And once you get more than $1, like, $1.02, $1.25, or something like that, now it's going to get narrower. That's just talking in terms of money. So you can understand, the 1 would be like $1, and this right here, your red one, it's going to open up and get bigger when you have less than $1. So you have less than $1, it could be any type of money. It's not going to be negative as far as that concerned. The negative would be this way, right, opening up or down. This is just talking about the number itself. You could have a half, and 1/2 as a fraction, 1/2. That's like half a dollar. That's like 50 cents. It's going to still be wider. You're still on the red part. But as soon as you get more than $1, if you get $2 or $3.50, well, now you're going to be, 3.5. You're going to be more. You're going to be thinner and narrower. So that's just kind of trying to explain the difference there. All right, let's go ahead and look at our extra practice. We'll look at these real quick here before we do that, just to see how we graph this 2x squared, and then we're also going to compare it to the parent function. We would want to make a table of values. That's the one thing we're going to make sure we do. Make a table of values, complete that table of values. So we choose the x numbers, and then we plug those in, and we can put 0 here, 1 here, 2 here for x, and then just evaluate that to get the y numbers. That's how we do that. As you can see here, if I try to evaluate for 2, how do I get 8? If I plug 2 in here for x, 2 squared is 4, and then 4 times the 2 in front would give us 8. That's how we do that. It's very simple. And then we're going to plot those points on the graph, so we go ahead and plot them. That's going to be our blue one here. The black one is the parent function, just the x squared one. Now the parent function always has a very parent pattern, and you want to know this parent pattern. Starts off obviously at 0, 0, but then you're just going to go 1 unit to the right, and you could square that. 1 squared means you're going to go up 1, and you could put a point there. Then you can go 2 units to the right, and you square 2. 2 squared is 4, and you can go up to 4, and you can see there's a point there. If we went over to 3, and then 3 squared is 9, we can go all the way up to 9, as you can see. There it is at 9 right up there at 3. And you do the same thing this way. You go 1 this way, go up 1. Go 2 this way, 2 squared is 4, go up 4. Go 3 this way, 3 squared is 9, and you can go up 9. That's the parent pattern for a quadratic. Just go 1, 2, 3 from that 0, 0 point of the vertex, and just square each of those to know how much to go up. That's your parent pattern. So you can always draw that very quickly and very easily. But now with you plotting these points, we get a parabola. It's actually narrower and thinner. You can see that because your 2 is more than 1. That's like $2, right? So we know we're going to be inside of our parent function. It's narrower. And so we can see what we would say there is that the graph is narrower, and we could say that that's a vertical stretch by a factor of 2. And that's kind of more, we want to get more of a technical term. Narrower is a term we can use to describe it, but actually the technical word and technical term that we want to get familiar with is a vertical stretch. It's like you're stretching the function a bit, like a rubber band or something. Let's take a look at this next one. This one's got a negative 1/3 in front of x squared. Okay, well that's going to be, we do our table of values here, picking some numbers for x and then plugging those in to get some numbers here. Now notice that we want to be strategic about picking numbers. We didn't use the same ones as before. Since the 3 is at the bottom, notice that we would pick a 3 and a 6 here, because 3 can cross cancel with 3 and 6 can cross cancel with 3 as well as we work that out. So as we do plug in 3 here, 3 squared is 9, and then 3 and 9 can cross cancel as you multiply by the 1/3. If you plug 6 in, 6 squared is 36, and you can cross cancel 36 and 3 as well. So you want to be strategic about that when you have a fraction here. You want to make sure you can choose numbers that you're going to eventually cross cancel with your denominator. And so now we would plot these points, and we can also draw our parent function here in black. There it is again, just going 1 unit to the right. Now it's actually, each box is worth 2, as you can see here. Be very careful about that, because sometimes each box is 1, but this one, each box is 2. So actually when we go to 2 here, 2 squared is 4, we'd go up to 4, and there you can see that's where you would be. Your blue one here is the one we have from our just plotting all of these points. You can see it's going down. How do we know it's going down just from the graph? Or from the equation here? It starts off negative. So since it's a negative in front, we should have known that it's going to open down. And then the 1/3, that's less than 1, so that's like some change right there. You have less than $1 basically right there, and so you know it's going to be wider. It's also wider. And so that's what they're going to be saying here. Opening down means there's a reflection over the x-axis. That's what they say here. That's the technical way of saying opening down. Yeah, we can describe it as saying it opens down, but the more technical way is reflection in the x-axis. And then the fact that it's got the 1/3 here, you can say, yeah, it's wider. Okay, that's the way we could say it. We could say wider, it says it right here, but the technical way would be to say that it's got a vertical shrink. So it's actually shrinking kind of towards the x-axis. It's getting closer and closer to the x-axis as that number gets smaller. Right there with the 1/3. If we went to a 1/5, that's going to be even closer to the x-axis. A 1/10 would be even closer, and so on. All right, so let's go ahead and try some problems now. 3 through 4. Now I'm just going to move my way through this, but what you might want to do is with each screen you might want to pause the video, and then try these on your own first, and then see if you can do them correctly by playing it. But I'm just going to move straight through all these problems, but I think it would be helpful for you to try these on your own to see, are you able to plug these numbers in, evaluate these correctly, and plot the points and be able to compare it correctly. And then you can play it to see what, if you did things correctly or if there's something maybe you missed. All right, so with number 3, it says 5x squared. Alright, I had to turn on my thing to write on it. So here we go. With 0, if I plug in 0, first things, here's our numbers that we're going to choose. I gave you the numbers to choose. So if I plug in 0, putting 0 here, 0 squared is still 0, and 5 times 0 is 0. So we should always get that as our vertex. Remember, we know the vertex on this one is going to be 0, 0. So we'd start with a point right here. So that's the thing about this one. What's the vertex of this? We know it's going to be 0, 0 of this function. With all of these, it's going to be 0, 0. If I plug in 1, putting 1 right here, 1 squared is 1, and then 1 times 5 would be 5. So 1, we're going to go up 5, 1, 2, 3, 4, 5, putting it right there. If I put negative 1 in here, negative 1 times negative 1 would be 1 again, and then 1 times 5 would also be 5. We're going to get the same number there, just on the other side because of symmetry. Remember, the axis of symmetry is going to be our y-axis going right through here. Now if I did 2, if I do 2 squared is 4, and then 4 times 5 is 20. 220, that's going to be off my graph. It's going to be way up there. And then if I put negative 2 here, negative 2 squared is 4, and that's also going to be 20 as well. But here's my graph. We're just going to kind of make this a U shape, just maybe come down, decreasing, and then going back up, increasing. What we're trying to do is not make it a V. And so it'll keep going up and up as we do this. And we don't want to get over here. We don't want to get to 2 because we're not going to get to 2 until we get to 20. So it's definitely inside that 2 there. So not the best looking graph, I know, when you're trying to draw it on freehand. Mine's not so good. You're trying to make sure you round this a bit there at the bottom so it's not a V. That's the main thing. We don't want it to be a V shape. We want it to be more of a U shape. Alright, so now what we see is if we compare it to the parent function, so remember the parent function would just be this. We started here at, we'll do the parent one in blue, we go 1, 1 right there, and then we go 2 to 4. Remember 2 squared is 4, 1, 2, 3, 4. We can do the same thing, negative 1 to 1, and then negative 2 up here also to 4. So that's going to be our parent function. So you can see this one definitely is narrower. I'll just go up to there. So you can see that this one is definitely inside here. So I wrote down the technical words. It's one of these it's gonna be one of these. Is it a reflection in the x-axis? No, it's still going up. Okay. Is it a vertical stretch? Yes, it is a vertical stretch for this one. This one is a vertical stretch. And we could say by what, though? In this case, it's going to be by the number 5. So we could say by factor of 5. That's what we would say on this one. All right, so number 4, we come to this one. Same numbers we're going to plug in. 0, it should be 0, 0 as well on this one. So we plug in 0 here. We're going to basically, 0 times a negative 4 is 0. So we're going to put 0, 0. Now notice the way the graph even is here, we should be opening down. We know we're going to open down on this one. This one opened up. So this one opens right here up. This one we know is going to open down because of the negative. That's why. So when we plug in 1 into this function, so that's going to be 1 times negative 4, that's going to be negative 4. Plug in negative 1. When negative 1 squared is 1 times negative 4 is still negative 4. So we go 1 unit each way from that vertex point, we're going to get the same number. So 1 to negative 4, and then negative 1 to also negative 4. If I plug in 2, 2 squared is 4, that's going to give me negative 16. Negative 2 should give me the same thing, going the other direction, same amount of units from the, well, we don't have 16 on here, so we're not going to plot that point. So this one, again, if we just draw this the best we can to make a U shape, so maybe coming this way, U shape around, and then coming down. That one was a little better than my last one. And so we're not going to get, we can keep going all the way down, but we don't want to get over to 2. We don't want to cross this 2 because we're not going to get to there until 16, which is like way down here. So I can keep coming down over here. I don't want to get to the negative 2 either. And then our parent function, remember the parent function would be going this direction. So if I just did the parent function, that'd be 1, 1 right there. Negative 1, 1, it would be doing something like this. This would be our parent function. So 2 things. On this one we could see it's definitely got the reflection in the x-axis. It's opening down, so technically we're going to say that, yeah, it's got a reflection in the x-axis. It's also got a stretching as well because this 4 is more than 1. When it's more than 1, it's going to stretch. So it's a vertical stretch as well. And in this case, it's by what? It's by 4. We're stretching it by 4. This one was stretched by 5. So we would say by factor of 4. By a factor of 4. All right, let's move on to the next one. In fact, I'm going to pause here really quick for our joke of the day. So why was the Energizer Bunny arrested? Why was the Energizer Bunny arrested? He was charged with battery. He was charged with battery. If you're not familiar with battery, battery means that he hurt somebody, hit somebody, beat somebody up. But yeah, Energizer Bunny is charged with battery. All right, moving on. Jokes are just too much. Okay, let's go on to number 5. Number 5, we just have a negative x squared. So again, we're starting with the same numbers here. 0, 1s, and 2s. So starting with a 0 right there. So I'll do that in red again. I'll do this first part in red. So starting with 0, 0, that's going to be our vertex. Remember, this is our vertex. You got to get familiar with that word. Vertex is the 0, 0. We know that's the middle one. There's nothing else. When we get to the ones that we're going to see, we're going to have a plus a bx plus a c. Then that's when our vertex moves around. But for right now, when it's just going to be our first single term here of the x squared term, it's always going to be 0, 0. When we plug in 1, that's just going to be negative 1. So now we have negative 1. Plug in negative 1, we're going to get a negative 1 again. So you can see when we go 1 this way, we're going to go down 1. Go 1 this way, we're going down 1. Plug in 2. If we plug in 2, 2 squared is 4, and then times negative is negative 4. Same thing, negative 2 squared is 4 times negative negative 4. So we go to 2, 1, 2, we're going to go down to 4. 1, 2, 3 to negative 4 there. and go 2 to this direction on the left, negative 2 here, we're going to go 1, 2, 3, 4, going down 4 to negative 4. Now I'm not labeling these axes, and you can do that if you like to label this. If you want to label this like negative 2 over here, negative 2, that's fine. I don't want to put too much on here to get you confused. So now we have this U shape to draw. So I'm going to draw it going up. Make sure you make it a U here, not a V, because a V shape is a different graph. We could even go to 3. If I went to 3, 1, 2, 3, I know I'm going to go to 9 because it's the same shape as the parent function. So it has that parent function pattern, it's just going down. So I can go 1, 2, 3, and then 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 would be all the way at the bottom. So I don't want to cross this 3 until I get to number 9 right there. That's where I'm headed towards. Same thing here, 3, we're going to go all the way to the bottom. So at negative 3, we're also at negative 9. And we just want to put the arrows on the end. That's what I'm doing there at the end. And now for our parent function, be good for you to draw it as well. Again, it would just be going 1 to the right, up 1, 1 to the left, and up 1. That's all we can see for now, but it's going to do that. It's the same shape, so there is no stretching or shrinking on this. It's the same shape. There is just the reflection because it's now opening down. Right? We know it opens down because of the negative sign. We know that from just looking at that. And so what we'd want to say to compare it to the parent function is that there is a reflection in the x-axis. On number 6, we can also see this one's opening down also with the negative in front of the 7. So that one opens down. When I plug in 0, we're going to get 0, 0 again, whereas we always are going to get here for these ones because there is nothing else past it. There is no plus or minuses of any other terms. And so we can start with 0, 0 as our vertex. Again, that is our vertex. We always want to identify your vertex first. Whenever you draw any kind of problem, as we get further down in chapter 8, we have to always identify that vertex first. It is our kind of our starting point. There's always a starting point to every single function that you're going to graph. When we graph the linear functions, there was a starting point there of just the y-intercept. That was our starting point on the linear ones. Well, on the quadratics, it is the vertex point. We need to start with that one. And so now when I plug in 1, we're going to get negative 7. Plug in negative 1, we're also going to get negative 7. If I plug in 2, 2 squared, that's 4. 4 times negative 7 will be negative 28. I'm not going to be able to graph that one. And I'm going to get negative 28 also with negative 2. When I go that direction, 2 units that way, I'll get the same thing because of symmetry, remember? That's why we're getting the same 2 numbers here. So when I go to 1 this way, I'm going to go down 7. 1, 2, 3, 4, 5, 6, 7, and negative 7. So this is actually the thinnest one, or the narrowest one we've seen so far. Go to negative 1, we're also going to go down to negative 7, and we're not going to be able to plot these two. Negative 28 is just too far down there. So now I'm going to bring it up, try to make it a bit of a very thin U shape. So U shape here. Now it's very hard to do that sometimes. And then come on back down. Come on this side of that one a little bit, not too much. Just one little bit on this side of that one line there. Alright, I know it's not the prettiest graph, but you get the idea. That's what it will look like. You can see a very clear one if you were to use a graphing calculator. And then our parent function again on this one would be doing the same thing. 1, 1, negative 1, and 1 as well. So this one, the shape changed. It has the reflection because it's opening down. So it has a reflection in the x-axis here. And it's also narrower, which means it's stretching. So it's stretching on this one as well. And what is it stretching by? It is stretching by a factor of the number, the A number, which is 7, by a factor of 7. Now we won't say negative 7. The negative sign is the reflection part. The number is the vertical stretch by that number 7. Okay, even though it's opening down. All right, moving on to our next two. 7 and 8. So 7, again, we can see this one's opening down because it starts off negative, opens down. And if we plug in 0, we're going to get 0. So again, 0, 0 will be our vertex. It's our starting point always. That's why I put that on the top there, just so we start with the vertex. You get used to starting with the vertex point. Now, if you do a table of values, you may not have the vertex at the top. But on these ones, I knew I was going to put 0 on the top, and I'm going to get the vertex when I do that. So you always want to find that vertex point. There will be ways that we'll find it later in other functions, in other ones we do. When I plug in 1, it's going to give me a negative 1/5. When I plug in 1. When I plug in negative 1, I'm going to get the same thing, a negative 1/5. When I plug in 5, now notice I chose 5. I didn't choose 2 this time because I'm trying to be able to cancel it down here. So when I plug in 5 here, 5 squared is 25. So it's like negative 1/5 now times 25. And I can put this 25 over 1. 5 can cross cancel with that, so that's a 5 now. So basically I have negative 1 times 5 is negative 5. We would get the same thing with this one as well. So when I plug in, when I do it a 1, I'm going to come down just a little bit here at 1/5. Not very far. Same thing here. I'm going to be just a little bit there at the negative 1/5. When I go to 5, so 1, 2, 3, 4, 5, which is on the side here, here is where I'm going to be at negative 5. So 1, 2, 3, 4, 5, and right down to here. 1, 2, 3, 4, 5, yep. So I go to the edge here, I'm going to go down 1, 2, 3, 4, 5. Now we could try to get something here in the middle of this. If I tried to maybe do something somewhere in the middle, maybe like a 3, if I wanted to try 3. If I plug 3 in, where would 3 be? If I try 3. So that's going to be a negative 1/5, oops, maybe 1/5, times 3 squared, which is 9. So it's really going to give me a negative 9/5. 5 goes into 9 one time, so it's going to be like a negative 1 4/5. So if I went over here to 3, 1, and this is going to be on for both of them, 3 and negative 3. It's going to give me the same thing. So if I come over here to 3, so there's negative 1, negative 2, 4/5 would be just right about in there. And same thing here, 1, 2, and then this would be 1, there's 2, it's right a little bit before that 2. So it kind of gives you the idea now of the way we would go. So let's go ahead and draw it from here. Wider ones are a whole lot easier, as you can see, to draw than the narrower ones. Narrower ones are much more difficult. Put your arrows on the ends. Now if I was to do the parent function again, I'm going to go to 1 and up 1, 1 and up 1. That's just for the first little bit there. Goes up like that and that. So you can see obviously we're getting a reflection here. We knew that from opening down. So when we're comparing it to our parent function, the most basic one, it's a reflection of that function. It's also wider. So when it's wider, we don't say stretch, we say shrink. It's actually getting closer. It's shrinking down towards the x-axis here. So it's going to be a shrink. And we can say, okay, it's by what though? By a factor of the a number. In this case, it's a 1/5, not negative 1/5, just say the 1/5. By a factor of the number 1/5. That's what we're shrinking by. The negative sign is where we talk about the reflection. The 1/5 is when we're talking about the stretching or the shrinking, in this case the shrinking one. Number 8, we have 0.6 here in front. It is opening up because it's positive, so we can see that. This one opens up. When I put in 0, I'm going to get 0 again. That is our vertex again. So our vertex 0, 0. Now notice I'm putting 2s and 4s here. I'm trying to be a little strategic a little bit on this one. We can get things even in the middle if we want to. If I could do 1s, I can do a whole bunch here if I wanted to. But if I do 2 and 4, I think that'll give us some good ones. So if I plug in 2, 2 squared is going to give me 4, and then 4 times 0.6. So 4 times 0.6, just 4 times 6 is 24, so with a decimal it's 2.4. And it's going to be 2.4 also when we put negative 2 in. When you plug in 4, 4 squared is 16, and then 16 times 6 is 96. With one decimal place, it's 9.6. So 9.6 there. So let's go ahead and plot these points. So at 2, we're going to go up to 2, 1, 2, and then 0.4. So 0.4 is not quite halfway. So right there. When I go to negative 2, same thing, not quite halfway. When I go to 4, so that's 2, 3, 4, I'm going to go up to 1, 2, 3, 4, 5, 6, 7, 8, 9. 9's at the very top here, so it's going to be just a little bit higher than that for 9.6. Same thing here, just right above here, just a little bit higher. So that's how we can kind of go. If we want to get something maybe more in between, we could look at where 1 would be and even where 3 would be. Like if I did 1, that's going to be at 0.6, so it's going to be just at 0.6, which is a little bit higher than half there. A little bit higher than half is at 0.6. If I plug in 3, that's 9 times 6 is 54. And then with one decimal point, that's 5.4. So if I go to 3, 1, 2, 3, 4, 5.4 would be just a little less than half there. Same thing over here at 3. 1, 2, 3, 4, 5, and then a little bit less than half for 0.4. So that the more points, as you can see, really help you see the shape. So I did 5 here. I would like you to do even more to see even the better shape to even draw this. So you can always do some of those extra ones. So as we come down, make sure we're getting the U shape here at the bottom. Coming back up. This is here where we're increasing on this side. Remember I was talking about increasing and decreasing. We started decreasing, and on this side of the 0, we're increasing as we go up. So it's almost like if you were drawing it, starting off on the left, for increasing and decreasing. And for the parent function, so I do a parent function here. I go 1, 1, negative 1, and 1. If I go to 2, it's 2 squared is 4. So 1, 2, 3, 4. And this one, 2 this way. We're going to also go 4. And so we can see on this one, here's our parent function. So the parent function, so this one is wider than the parent function. It's going the same direction, so there's no reflection. We don't say reflection on this one because it's opening up, which is the same direction the parent function goes. But it's wider, so there's no stretching. It's got to shrink again. So this one's got a vertical shrink. Vertical shrink by what? Well, we would say by factor of the number right here, that number of 0.6. Of 0.6. That's how it's shrinking by. Alright, so that's it for the graphing. There's a couple more questions here. Let's go to 9 and 10 and take a look at those too. And in fact, before we get there, let's just take a quick look at this example. I just wanted to show you the picture of this, because where do you see parabolas in real life? And this is really kind of where we see them. As you notice, if you can identify what picture this is, see if you can think about what's a picture of that. That is a satellite dish. Now, you should be familiar with satellite dishes. There's a lot of houses that have satellite dishes to get in, cable to their house. We have satellite dishes out in space. We have satellite dishes on the ground down here. So satellite dishes are a way that we understand parabolas, because it's the shape of a parabola. It's a big kind of like a bowl, but the cross section of it, if we were to slice it, just like slice it with a knife or something like that, we would get a cross section of a parabola. So that's why parabolas here are very important to understand for even engineering. A lot of shapes are shapes of parabolas. This is just one of those shapes I'm not going to go on into showing you much of this, but just so you can understand, where do you see a parabola in real life? Well, whenever you see a satellite dish, you'll see a parabola. Another one is whenever you see a flashlight. That's also a parabola as well. Whenever you see a flashlight, think of a parabola. Parabola, you had to understand parabolas to be able to create and make the flashlights. All right, so here it goes with 9 and 10. It says, determine whether the statement is always, sometimes, or never true. Explain your reasoning. It says the graph on number 9 here, the graph of g of x. G of x, again, is just another way of saying y. It's just a function notation of what we've been learning here. The ax squared is wider than the graph of the f of x equals x squared, which is your parent function, when a is greater than 0. Okay, well, when a is greater than 0 means that it's positive. Okay, so is it always going to be wider? So is it always going to be wider when that's true? Is it sometimes going to be wider, or is it never going to be wider? Well, in this case, remember, when this means that a is greater than 0, it just means it's opening up, which is the same direction that our parent function is going. So it could be wider if a was greater than 1 as well. If a was greater than 1, then it would be wider. So that's why sometimes. So if it's like between 0 and 1, if it's just change, then the graph would be wider. So that's why sometimes is our answer on this one. It's sometimes if it's this. The graph is narrower when the graph of f is greater than 1, but it's wider when it's 1. When it's greater than, or it's between 0 and 1, we can know it's going to be a wider graph. So sometimes that would be true. This one, number 10, the graph here, same kind of question, is narrower when of the parent function when the absolute value of a, which would be actually just the number, is less than 1. So when the absolute value of a is less than 1, so that means that it would be not negative, okay, because absolute value would always be positive, but when it's less than 1, that means it's going to be like, in the point where it's like 1 penny to 99 cents area, and that's going to be wider, not narrower. So it's never going to be narrower when it's less than 1, when it's in that section of kind of like right here between 0 and 1. So that's why it's never on this one. It would always be wider. So if this was wider, it would say always. But since it says narrower, it's never going to be narrower. All right, so you can go ahead and write those down for 9 and 10. And that concludes our lesson here for 8.1 on this, the very basic part of getting to understand these quadratic functions, how to graph them. And we'll continue on learning more about these as we go through Chapter 8. So you guys have a good rest of your day, and I'll see you on the next lesson.